Gears may look simple at the first glance, but their geometry is one of the most elegant and powerful concepts in mechanical engineering. At the heart of every gear tooth lies the involute of circle, a curve that ensures smooth and constant transmission of motion. But what happened below the base circle, this is where another fascinating shape appears, the trochoid, generated by the actual cutting process. In this video, we'll break down these two fundamental curves, understand how they are formed, and see how they define the performance of real gears. Let's dive into the geometry behind of the most essential component in engineering. And to follow the next video, don't forget to subscribe to my channel, like this video, and ask any question. Let's start this video. So as we have seen in the last video, we have seen all the parameters of the gears. We have, for example, the module that is important to design any gear, number of teeth, and so on. And we have looked in all these parameters. Today, as I told you, we will attack another thing. It is the geometry of the tooth. So to draw to do a gear, we have to draw here an involute and a trochoid in here. So we will start this by this involute. So to draw it, we need the number of the teeth and the base circle. Here we have 18 teeth. Then we will need the circular pitch. So it is here. We can calculate it. P is equal to pi multiplied by m, the module. Then we can calculate the base circle by multiplying the pitch circle, that is also important, by cosinus of alpha. So the base circle is lower than the pitch circle. Then we measure between 3 and 6 pitch length. It depends of the precision you want to have. Then we'll mark in the n-1 tooth a constriction line to start the tooth arc that is tangent to the base circle. So we will draw a line that is tangent to this base circle. Then we will do the same thing. We will add a second line with 2 times the pitch, the pitch here. We have 1 time the pitch here and 2 times here in the n-2 tooth. So we want to draw this involute. We have the n tooth and we have the n-1 and the n-2. Then we will go to the n-3. We will do the same. Here we can draw it with using the spline in your software or your CAD software. It depends of its name, but in general it is spline. Then we will repeat it for 3, 4, 5, and 6. Then now we will see the profile between the base and the root circle. In this picture, we have a gap region here. They show it, gap region, difference in shape. And here we have gap region. They call it fillet area. It means that they just uh, draw a portion of circle here. So between the base circle and the root circle, there is no involute. We can modelize it by an involute, but it is not really real. But in reality, it is a trochoidal root in general generated by the motion of the cutting tool, hub or rack type cutter. So when the cutter cuts this gear, it will create this type of shape. It will help also to so this tooth will take higher power and higher forces and higher constraints. So it is done with the shape that we call a trochoidal, but it is not a fillet. So a trochoidal is a curve generated by a point outside or inside the cycle rolling along a straight line. So it is a curve by a point outside like this or inside like this by a point of the cycle that is rolling on a line. So we have this line and the a cycle will do this shape and do this if it follows this line, or this it will create another shape like this. So this is a superior trochoid, this is an interior trochoid, and when it is exactly here we call it a cycloid. In the part outside, we call it superior, and in the inside, we call it inferior, as it is here. Inferior or interior, it is the same. So why a trochoid? When a gear is manufactured by generating process, the tool removes material while rolling. The result in shape is this shape here. The tooth root is an envelope, so it's a trochoid. So it is not a simple theoretical shape like a circular arc, as it is generally done in CAD, but it is a special form that we call a trochoid, and it is here in the root. So in practice CAD, you have 3 levels of accuracy. You can use a simplified method uh, with doing just a portion of circle like this or like this, or a root connection using a circular arc, root fillets radius, so we can extend just this like that will go like this, or do a symmetry here and turn it directly with using Involute, for example. It is sufficient for standard mechanical design, 3D printing, or general studies, just to have an idea. For example, if we want to do FEM, then we can use a realistic method. It is industrial method. So we can do an involute, as I told you, but it is not really an involute and not really precise. Uh, or connecting with using a true trochoid, that is the most precise thing to do. It is useful for precise simulation, or in critical practices like aerospace or high performance transmissions, like in special cars like Formula One cars. So a clear summary: bicycle, i- it is an involute, and from bicycle to the tip circle, it is an involute. From the bicycle to the root circle, it is a trochoid, not an involute. And for an engineering tip, or I will give you an engineering tip. In 90% of cases in CAD, you can use an involute plus a fillet radius, and you can do your study, or your machine can work if you want to do it with 3D printing. But the true trochoid is rarely modeled unless high accuracy is required. I have a bonus tip. It is that uh, you can use some softwares that they are in Google, where you can give just the data, and it will design to you directly the gear. But we will see this in the next videos. Thank you for watching this video. Don't forget to subscribe, like this video, and ask any question in the comment section. Tschüss.